basically. And after this, you deposit metal layer. Metal layer means, let's say if you want to fabricate silicon beam, so you do evaporation, thermal evaporation or sputtering of these material on the top of it. Since this layer is already there, you will see that you will get a layer which looks like this, right? It will come and sit here. Now the next target is you have to remove this so that it will come out as a cantilever. So you have to again remove that, and like you will get a layer of this kind. Okay, so that is using dry etching or something. You can do it even using wet etching. Many people try to do it. So this is all etching mechanism through which we try to remove these sacrificial layers. They are usually, when you buy a silicon wafer, you need to tell what should be the thickness of this sacrificial layer. Based on that, they will deposit silicon oxide or nitride, and then they will provide it to you. Okay, or you can buy bare silicon, get the deposition of these layers in during oxidation, and after that you can go through this process. Now while you go through these processes, what you really get, you get uh, like suspended cantilever beam, right? Which looks something like this. Can you see that? Something like this. Now in this particular picture you can see some of the beams are straight as you designed, right? But some of the beams are bending upward. Why so? Because when you deposit these metals using thermal evaporation, thermal evaporation technique or RF sputtering, or through thermal means, so what really happens, some kind of stresses are uh, developed inside, and when you bring this particular substrate or die out of the oven, what really happens, your structure will try to come in equilibrium with the surrounding, and when it tries to come in equilibrium the surrounding, because of the stresses which are inbuilt, it will bend it upward. Okay, so that it now comes in equilibrium with the surrounding, but in a different state, right? So these effects are primarily due to the stresses which are developed during the fabrication processes. So we need to be careful with, we have to standardize the process so that such kind of thing doesn't really come up, or different types of beam needs first, we need to check which using let us say some process flow, what are the defects that we may get, and by following the guidelines of those fabrication only we should try to design our sensors. Okay, so this is another effect that you see. And yeah, the bending, these are bendings are due to because of the residual stresses. So I took this slide from Professor Prem Pal, who is my colleague at IIT Hyderabad. So similar to that, there is bulk micromachining. What is the difference in bulk micromachining? So in this case, bulk micromachining is like you have a bulk wafer, right? And you are trying to fabricate a structure out of that bulk. But in the previous case, what we did, we uh, in the previous case, we layer by layer like fabricated a cantilever. But in the bulk, we will fabricate cantilever out of your given substrate. Okay, so what it involves, it involves removal of the bulk, removal of the part of the bulk substrate. In the previous case, addition of the material on the top of the substrate. Okay, so let us see how it works. So again, following the same thing, you will do first of all deposition, then patterning, right? For deposition of sacrificial layer like oxide or nitride, then patterning using laser or e-beam or ion, right? So focused ion. So after that you develop it so that you will know where like wherever this patterning is being done, that will be left out. So based on whether you are using positive photoresist or negative photoresist, so corresponding to that the etching will happen. So after going through this process, what you get is, let us say, the material which is not exposed, this will get start etching away, right? So when it etches, you see that sometimes it doesn't etch completely. Some of the material underneath will remain there, right? So that is a problem when you, so it means that if I try to etch this with respect to KOH is your etchant, you will get this problem, right? And if you see it from the top, you see that how this material remains over here, right? Similar to that, if I use, let us say, some other etchant, which is TMAH, so in that case, you see that the material is removed completely and your cantilever is suspended, uh, as you thought of, right? So it means the full length is available now, but here you will get only the effective length smaller than the designed one, and that way it will change the resulting frequency, and this one will give you the same frequency, right? So we have to be careful with these process steps, the solution that you are going to use for etching these devices. uh, and the third one is your wafer bonding based device. So what you do, you first take two wafers, right? One wafer is this, another one is this, and you do the deposition, thermal oxidation of these two, right? And then you, what you do in one, you create a cavity, right? You do some etching and create a cavity, and on the another, you, what you do, you take it and then bond them together. So after you do bonding, either you can do direct bonding. After you do this bonding, then you start thinning the top surfaces using etching, of course. So this will keep on becoming thin and thin. Now you have to keep on etching it till you get the required thickness. Okay, this is called your required thickness. Okay, so after you get that, what you, after you get this required thickness, you will have to uh, etch this particular, like open up this one and then start etching it. So here you can see there is a lithography you did and then etching this particular portion to create a structure which is similar to your cantilever beam. So through this process you see that you get a very thick beam that can be fabricated, and this is how basically it is being done. Okay, so these three processes are quite like in, uh,
जल्दी तो है ना उस पे
these three processes are very important from the point
मैंने
of
शेयर
view
की थी
of your
वासी
MEMS.
नंबर लिखेगा कौन सा
Can
जो
you
नंबर लिखेगा उसमें मैं नहीं भेज देता हूँ
can you
सीरियल
mute, can you
हाँ
mute
सीरियल वाइज जो है ना हाँ वही भेज
Hello.
हेलो
can you mute some participants who are speaking? Okay, so
Yes, sir.
now,
Go ahead, sir.
yeah. So now, what really happens during this etching when you just try to etch some of these devices which are quite thick? Okay, so there is a process called DRI. So when we try to do it, we do some like alternate processing. Okay, and in that, due to that, what we can come across is, you know, some kind of scalloping along the thickness of that structures. Okay, so you can see there is an scalloping along the thickness of these structures. And second thing that may also happen is the slanting. Okay, because the etching is starting from here, so you may just having a slanting of these. And third case, you can have a slanting as well as you will have all this which is coming up, right? So because of all these effects, what happens that many the electrical forces that are being generated uh, in the devices, that may vary. Then stiffness that you are going to calculate, considering that it is uniform, that may vary. Okay, so those defects need to be considered at the design stage when you are doing this design. So what are the tools which are available from where you can learn? So the question is, we have lot of uh, like uh, we have lot of instruments through which we can do this fabrication, but they are very costly, and you can't really establish such kind of fab everywhere in India or in each and every institutions, because it requires an outlay of, let's say, 50 to 100 crores to completely fix up this whole facility, and there's not and then after that you will have to maintain them. So those who are willing to just start, they can always start with some softwares. They can start theoretical work, then try to contact the fab. So there are many fabs, like we do have fabs. Then there are fabs in ID Bombay, at ISC Bangalore, at many places the fabs are there, which they allow access based on some per hour or per samples that they want to they can fabricate. So there are some rates that are being followed, and one can always do it. And so that is one way. Another one is, let's say, if you want to just start with the design, then what are the platforms that are available? For example, there are two important platforms. One is your Coventerware, another one is IntelliSuite, which gives you uh, like uh, give you some idea of how to fabricate these devices, because they have the process flow also. Okay, so for example, this particular example I am trying to explain, that was done in IntelliSuite. So here you can just see that this is a multi beams that is being fabricated. So here first, you can just see that, starting there is a deposition that is happening. Then after deposition, you can see there is a pattern transfer. So there is a photoresist. After deposition, there is a photoresist, and then pattern transfer will happen, right? And then etching will happen. There is a pattern transfer, and then you will do etching. So when you do etching, you will get these devices. Okay, and so that's how basically, and then complete after you transfer from here, you have to transfer, you have to do deposition of the metal on the top, and then again etching you will have to do to get rid of rest of the sacrificial layer. So that way you see that your hanging beams are there, right? Multiple hanging beams are fabricated if you completely etch it. And that's how you can fabricate it using these softwares, IntelliSuite as well as Coventerware. You can work in any one of them, and you will be able to follow step by step process of this surface micromachining and all. Okay, similar to this, if you the same thing, deposition, then this patterning, etching, then metal deposition, then etching away all the part will lead to give you, these are multi-stage one. That's why you have, first etching, then you do it again. So the multi-stage the fabrication process, or multi-layer, I would say that multi-layer fabrication process, where you are having in one layer you are fabricating, let us say, the pads. Another layer you are fabricating the beams, something you are fabricating, third layers you are fabricating the structure and all. So that way also you can do it, complete multi-step processing you can do using these softwares also. And the similar way you also fabricate it, of course. uh, for each and every fab have a different parameters. Okay, so we need to be careful. We need to know what are the process parameters of a given lab, and based on that only we need to tune our design. Okay, so before you start design, you should always look for in which fab you are going to fabricate, and of course, start when you don't have a name to fabricate. You can always start with standard dimensions and all that without considering many defects. But as soon as you know that you are going to fabricate this device in certain fab, so in that fab you can you should know what are the process control parameters, okay, and what are the constraint, and based on that you can include it in your design stage using these softwares also, or you can also do it in MATLAB. In fact, you can write your own code and do not just process, of course you can't really generate. Now let us say you are ready with your device, okay, you have fabricated it. Now you want to do testing. Fine. So how to do testing? So let us say this is your device. This is your how this device looks like. Here you are having like this is a plate, okay, and it is supported by four beams. Four beams, okay, and there is a bottom. Here is a bottom plate also, which is sitting, and it is connected with another pad, and this top layer I will connect it with another pad, okay. So this is one pad. If I apply voltage here, and the bottom one, right, let us say like this, voltage. So what will happen? This plate, which is supported by these four beams, one, two, three, four, it will move up and down, right? So when it moves up and down, so we can measure the oscillation from the top and know that what is the frequency at which it is oscillating, right? So the same thing is being done here. You can see this one is connected to the beam, this one is connected to the bottom of the beam, or the bottom substrate. So when the voltage is developed across the beam and the bottom, it will keep on oscillating. So here you can just see that this, and the measurement is done using laser vibrometer. So here you can just see that electrical excitation is being done between these two, and the measurement can be done. So after you excite it, your structure will start oscillating, and when it starts oscillating, you can measure it using the laser which is kept on it, right? And you will get a signal. You can get time signal, you can get frequency response, right? You can get phase response, etc. And then from there you will get frequency and damping, right? Frequency and damping. So so this is what basically. So but there are a lot of coupled effects which are associated with it. One is, first one is structurally they are coupled, so you can have a coupled mechanical effect or coupled structural effect. You can have interdisciplinary coupling, which is your mechanical or electrical. So that can be electromechanical coupling. There can be laser thermomechanical coupling, right? So all these will add more and more interesting effects in your devices, right? Since they are very small, they are sensitive to these small changes. So how do we see these mechanical motions? So this is what I was using it in the last, and all these structures we got it fabricated when I was doing my PhD at ISC Bangalore. So so this is one, then this is another. This is a torsion beam. This is cantilever. This cantilever we used from IIT Madras, and Professor Inakshi Bhattacharya, student, basically fabricated it. So with the help, so all these devices, give you a unique kind of uh, uh, motion. This will give you parallel motion, which is out of plane. This will give you angular motion, right? This will give you flexural motion like a cantilever. And here you can just see using this laser vibrometer that we are having at IIT Hyderabad as well. So this is called your junction box, and then your processing unit and signal generators, all are just fixed into this particular box. Okay, and from there, this is your laser source. There you can see your laser source, and with the help of this laser, you bring it into this head. This is called a scanning head, and then from here the laser right go through this eyepiece, right, and then it falls on the structure. So these structures are kept over here, and they fall on the top of it, and with the help of electrical excitation they will vibrate, and when they will vibrate you will be able to measure the response. Okay, so for example, how it looks like, so this you already saw, and for this you can see that there is a torsional kind of torsional motion, or the combined out of plane and torsional motion that is being shown. And in the cantilever case you can just see that this portion is in the first mode of operation, right? So this is what basically you can measure, and all these dimensions are of of the order of uh, 100 to 500 micron. So I'm talking about this length. So this scale is of the order of around 500 micron, I would say, and you can measure this with the help of this uh, like vibrometer. So what you basically get, so if you want to see it a little bit more carefully, so this is how basically it appears. This is your device, laser, here is your all probes, right? With the help of here you can do probing, and with the laser you can measure from the top of this device. So what you basically get, let us say for this cantilever, you get these three responses, right? One response, so this is your frequency response. Basically, it is called frequency response. So based on what is your range of measurement, okay, so you will get the peaks. So if you are measuring it over, let us say 10 uh, kilohertz, or this is like how much, this is a 900 kilohertz, right? So around uh, 900 kilohertz range if you are measuring, so you will be able to get first frequency, second frequency, third frequency. And how do you decide which frequency mode is there? So uh, through this scanning laser vibrometer you can do scanning over whole length of your cantilever, for example here, all over, and then you can generate the mode, and the mode will tell whether this is your first bending mode, or the second bending mode, or the third bending mode, right? So based on these modes you can decide what is your mode of operation for a frequency. So basically these devices are very handy, and they can be used to measure response, dynamic response of all these MEMS devices. And the typical frequency range over here is 43 first mode, 245 kilohertz second, and 690 kilohertz the third mode. Okay, now to understand as a designer how we are going to control these frequencies. So as I said, when you see a typical frequency response, you have a peak, and corresponding to that you get the corresponding modal frequencies, right? And then this width, when you take 1 by root times this peak, so you will get uh, this this length, and here you need to find out where is these frequencies are. So based on that you will have delta W. Okay, so this width, which is delta W or delta F, can be used to find different quantities. So first of all, after getting this frequency F or omega, we deal it with K and M, which is your K by M, and damping ratio, we know that it is C by Cc. Cc is 2 under root Km, and the quality factor we get directly from here. Okay, so with the help of this, so omega n is this, right? This is your omega n, and delta omega is this. So after we find out is omega n and delta omega, we will be able to find quality factor, right? And after finding quality factor, we will be getting the damping ratio. Damping ratio is nothing but C by Cc, or this uh, particular factor. And based on omega, we can find out our corresponding K and M, or whatever some of the some of the factors that you want to extract from the measurement. You can always get using all these formulations. Okay, so this is how we design our MEMS, and this is how we try to extract some of the parameters associated with it. Now let us try to see a little bit, go into a little bit more fundamentals. So if you are having like if you have to model cantilevers, so we know that since it is vibrating, we need to find the corresponding mass, lumped stiffness, and lumped damping parameter of this particular structure. And to do that, what we need to do, so let us say M is your total mass, rho BHL, but we know that it not whole mass is oscillating in the first pole, right? So corresponding to that, as I said, your effective mass is simply 0.24 times the total mass of the beam. Okay, it is not complete. So the M that you are going to use here should be around 0.24 times that. Similar to that, you can also find effective stiffness, and that effective stiffness will give you this 3 EI by L cube, and then you can substitute BH cube by 12, and that way you'll get 4L cube. Okay, so you are done with your M, you are done with your K. You can substitute this one over here and compare this theoretical F, F that you are going to, sorry, this is your omega, theoretical M that you are going to find, that you should compare with the experimental omega to see that how much deviation is there in your fabricated structure as compared to the design frequency. Okay, so that way we get a confidence on these fabrication processes. We get confidence whether we are getting exactly the same parameter that we are thinking of, or we are getting different parameters which are there, right? Then the third one is your damping. As I said, the damping is dependent on many factors like structure, fluid, and thermoelastic damping, support losses, etc., right? Now, so based on all these studies, what are the parameters, performance parameters in MEMS devices? Okay, so when we look for, we talk about MEMS devices, their sensitivity and the bandwidth. These two are very important thing, because bandwidth, like to what extent my structure can work. Sensitivity means how small, how small you can do the measurement. So it means that all these factors are functions of many different quantities. For example, how you are exciting your structure, whether you are exciting it using piezo actuation, or you are doing electrical actuation, or you are doing piezoelectrical or magnetic actuation, right? There are different actuation mechanism that you can think about. So all of them will have a different effect. So that needs to be understood. That needs to be understood. And then we need to know what are the frequencies at which it will operate. So we need to find out effective mass and stiffness. Third thing that I will be talking about is the non-linearity. Okay, so this is called your linear response. Okay, this is your linear response. But when you talk about non-linearity, it means that you are exciting your structure at little bit higher energy, right? So this is what is called your non-linearity. And then you get your damping, different damping mechanisms. Whether that damping is linear, constant, and non-linear, you need to consider that. 1 minute. Okay. So let us talk about first of all, after, so until now we discussed about the frequency, the fabrication. So first we discussed about uh, the how MEMS device work, what are the factors associated with it, and then we discussed about how it is fabricated, and then we discussed about how it is tested, right, and how do you get those parameters. And we now let us look at different tuning mechanism in these devices. Okay, so when you see these devices, as I said, uh, mostly when we talk about frequency tuning, it means we need to tune the stiffness, right? So in general, if you just take the device, it is omega is equal to under root k by m. If we want to do tuning because of the electromechanical, if we are exciting this structure electrically, so we have electromechanical effect. Okay, and that electromechanical effect may tune the frequency like this. So if you increase VDC in that actuation, you see that the frequency reduces, right? Because it is a minus, the frequency may shifts from this portion to this portion. Okay, so because of VDC effect, and that we call as electrostatic softening effect. Okay, this is called softening effect. And then after you put this, so this is one way of doing tuning. Second way is thermomechanical coupling. If you heat the structure, what will happen? Because of the temperature also it becomes soft, right? And then since it is k becomes soft, means k reduces, your omega will also reduce. And how it works? It works through this particular expression, right? So if you increase temperature, it means that your frequency is going to reduce. Now there is a third important mechanism. If you are exciting your structure at a higher amplitude, you get this nonlinear stretching effect. And this is stiffness. It means that there will be a tension that will be generated in the structure, and that will increase your Ka. Okay, so when there is a large stretching happening in a structure, it will increase your stiffness, and increase in stiffness means it will increase your omega. So now you see that there are very interesting effects. One is the stretching effect, thermoelastic effect, thermomechanical effect, and electrostatic effect. These two effects reduces the frequency, right? And this effect increases the frequency. Now, and if you just try to couple this and this together, you can get very interesting, tuning phenomena. For example, let us say here is the voltage. Okay, so this is your voltage VDC that you are applying to this device, and this is your structure. Okay, this is your structure, and what you are doing is, here is your fixed substrate, and you are applying voltage between this. Okay, let us say VDC you are applying. Now when VDC you are applying, it is getting stretched, right? How it is getting stretched? This portion, and also curvature is changing. So the middle portion is getting stretched, right? And the curvature is also changing. So they are all they all add, to, they all increase the stiffness of your structure. So there are two effects. One is stretching, in which your frequency increases, and there is another effect in which your frequency reduces. Okay, so electrostatic softening. So if I just concentrate on electrostatic softening, so what really happens? Softening means, if I start from here, right? This is your, when VDC is 0, if I start from here, if I increase this VDC, what will happen? Frequency will vary like this, right? So it is reducing, right? So this is your frequency graph, and the frequency reduces like this. Now, while if I see this stretching effect, what is happening? So VDC, let us say because of the VDC, but this gap is very large. It means that you are having this device and the gap is like this. Okay, so when the gap is large, this electrostatic softening effect will be weak, right? And when it is small, electrostatic effect will be significant, dominant. So in this case, if this gap is large and if you are applying voltage, it will still bend, it will still stretch, but the electrostatic effects in this case will be less, right? So let us say when you start applying VDC and electrostatic softening effect is negligible, in that case what will happen? Starting from this frequency F, your frequency will start increasing, right, as you are applying this loading. So this is your stretching effect. Okay, this is your stretching effect. Yeah, this is your stretching effect and this is your softening effect. Now if I try to uh, make like take the beam such that, you know, if I deal with the two modes, okay, two modes in which, so let us say it is like this. Okay, so if I take the width and stiffness, thickness T and width B little bit closer to each other, like B is let's assume is equal to 10 micrometer and T is 5 micrometer. Okay, and they are of the same order. In that case, what will happen? The modes which are about this will be somewhere here, right? Frequency F1. So if out of plane, if I'll call it as out of plane, or we can call it as out of plane, so that frequency, because B is more and thickness is small, the motion which is about along thickness, that will have lower frequency, so we will call it as out of plane frequency. And the motion which is along the width, okay, along the width, so we'll call this as in plane motion. Okay, so that will be higher because the B is more, so along this the B will act as thickness, right? And since this is bigger, its frequency will always be higher. So let us say this is here, is in plane, will come here. Now when I start applying voltage, okay, when I start applying voltage, and if I see that so let us take a cross section here, maybe with respect to that it will make sense more. So let us say this is your structure and this is your bottom one, and then you are having another like electrode. So you have electrostatic actuation here, and let us say there is no electrostatic actuation happening. Okay, no electrostatic, this is all grounded, but this gap is also very large. Okay, this is D, this is G, so D is much larger than G. Okay, then what will happen? This motion will be dominated by this voltage, right? This motion will be dominated by in plane motion, which we'll call as in plane, which we are calling this, and which is this. Okay, this is in plane. So in plane motion is dominated by electrostatic effect, which is this, right? Electrostatic softening. And out of plane motion, where the gap is very large, here electrostatic, even if it is grounded, your electrostatic effect will be less, right? So in that case, what will play? This stretching effect will undergo or will dominate over the electrostatic effect. So when you apply this voltage VDC, right, plus VAC something. So when you increase your VDC, what happens? We know that out of plane is dominated by stretching. So for stretching, frequency increases. So it increases like this. And for in plane, which is dominated by electrostatic forcing, like this, it will reduce, right? So here it will reduce. And what will happen? They will come closer to each other. If there is a coupling happens, so there is an anti-crossing region. this will just go like this will go like this, and this at this place both the frequency will become uh, very near to each other, and the exchange of energy from one mode to another becomes quite interesting. And that's how basically you can tune frequency. So here electrostatic stretching, mechanical tuning is here, which is nonlinear stretching, and here electrostatic tuning is there. And when you tune both of them, it comes closer to some point, so you can figure out it in which frequency range your device is going to work. And over the whole range you can tune your frequency. It can work over the whole range corresponding to the need of, you know uh, like the device. Let's say if the device has to operate here, you can tune your frequency such that your device comes here. You can do here. There are a lot of flexibility. Otherwise, if you can't tune, then device just will work here or here. That's it, right? So that's why the tuning is important. So you see that using all this, the very interesting phenomena can be observed, and then one can take care of it. Now coming to non-linear relay. So what I was talking about previously is mostly linear effects, but when we talk about non-linear effects, so whenever we talk non-linear, here we are mostly referring it to geometric non-linearity, right? Which is your uh, where there's a deflection based non-linearity, and mostly such kind of nonlinearity is captured by Duffing equation, where we have cubic nonlinearity. So you will see that in linear equation your inertial term is u double dot, which is linear, and then this is your damping related term, which is again linear, so velocity, and your deflection related term, if there is a linear spring, you just have this one uh, into picture, right? Omega 1, which is linear. And then if you are oscillating your structure beyond this thickness at a large amplitude, what will happen? This will introduce some kind of non-linearity. Okay, and this nonlinearity will make the frequency response look something like this. So this one is a linear response where your alpha c is equals to 0, means you don't have this nonlinearity, so you will get a linear response like this, okay, which is symmetric about this one. Now when your this particular factor is positive and is small, you see that this tilts, right? It tilts, and such kind of response is nonlinear response, but it comes with some kind of phenomena like this. So basically what really happens, you will see that in this nonlinearity, up to this the solution is stable. Then you have this one, and when you do backward sweeping, something like this, when you do backward sweeping from here, so it will again go up to this region and then jump at this point and start going this way. Okay, so your response, your device will be stable, will be stable over this region, but it is unstable over this region. So this is your unstable portion. Okay, so this portion is unstable, and this is the stable portion. All right, so that's why you see that there are dots which are available over here. So basically that's what is your nonlinear response, typical nonlinear response. And if your alpha s is greater than 0, you get it like this, which is hardening. Since the frequency is in the increasing side, we call it as hardening response, nonlinear hardening response. And in this case, since the frequency reduces, right, since the frequency reduces, so we call this kind of softening, nonlinear softening effect we call it. Okay, so here the frequency is reducing, so both of them a nonlinear response based on the sign of this alpha s, you will be either getting softening or you will get hardening. And in most of the structural problem, you are going to have only this this response, which is dominated. Okay, so that's how basically you model them using this Duffing equation, and there are different techniques to solve such kind of nonlinear equations, like perturbation method, right, which includes your multiple scale method, which includes averaging method, which include harmonic balance method. There is another method which is normal form method, which is quite accurate and popular. It can be also used for like strong nonlinear problems, right? So this is one type of nonlinear. Now there is another type of response that you may get, which we call as the parametric response, and many people are using such kind of response to get the, because why we are looking after the response, because the sensitivity of your device will be you can measure the response if it is um, sensible, right, if you can sense them. But if the response itself is very small, so the signal will be very weak and you will not be able to measure it. So with less force, how to improve the response is something that we also look for, and this parametric excitation adds value to it. Okay, so what is parametric? So in parametric excitation, you will see that, so this excitation that we discussed is called external excitation. Okay, here you see we are exciting it using external force, and that's why it is called external excitation, and the coefficients of all these terms are constant. Okay, these are constant. And how is the typical response of this? It first starts slowly building up, and then it reaches to peak near the resonance and start going down. Okay, this is a typical response of external excitation of a beam. But when we talk about parametric excitation, we don't have any monotonic rise. Okay, we don't have any monotonic rise, it isn't there. So in this case, first of all, I'll discuss about the equation itself. You see that the coefficient of u is a time varying quantity. Okay, so in this case, uh, suddenly when you vary this omega here, when you vary this omega, suddenly you see that corresponding to this, there will be a response. It's a very large response that you get. If you are having some nonlinear damping, okay, then you get the closed response. If you are not having nonlinear damping, you will get a straight response. And in this case, if you are having nonlinear stiffness, then you get the banding like this. If you are not having stiffness, it will be a straight kind of lines. Okay, so if you don't have any nonlinear terms, you get just this. Then there will be off, signal will be off, and suddenly you will get one very large response, and then signal will be off. Okay, that is the characteristics of parametric excitation. If you are having nonlinear damping, the loop will always be closed. Here, nonlinear damping and nonlinear stiffness both are there, that's why there is a banding basically, so you get a response of this kind. So why it is important? It is important because even with a small forcing you can get a large response, and for the closed loop it is important that you should have nonlinear damping in the system, and that equation is governed by Matthews equation. Okay, the previous one was your uh, Duffing equation. So that's what I was talking about through one of the examples. So this example, you can say that there is a fixed beam. Okay, this is of nano scale range, and it is excited electrostatically in this direction, and the bottom one is grounded. So this gap is very small. So you see that as the voltage is increased, its frequency reduces, right? Sorry, yeah. As the volt, 1 minute, as the voltage increased, the frequency reduces. So this is your voltage and this is your frequency. So the frequency, as the voltage is increasing, you can see that frequency is also, as the voltage is increasing, you can see the frequency is reducing. Similar to that for the out of plane motion, where this gap is very large and it is not electrostatically excited in this direction, only the stretching happening in this particular direction, but this mode will pick up that stretching and you will see that the frequency will start increasing. Okay, when the frequency starts increasing, what will happen? This is what I was talking about. If you bring both of them here, in plane frequency is reducing, out of plane increasing, and you have this anti crossing region where the coupling of these two modes happens, and that way you can think about uh, the different phenomena that occurs over here. And the width of this all depends on how strongly these two are coupled together. If there is no coupling, it will simply just go like this. If there is a coupling, then this gap increases. Okay, so these are the effects that one can see. As far as the non-linear effects are concerned, you see that when you excite a structure, so it will first have the planar mode, which will move like this, right? Then you have, uh, as you keep on increasing the excitation, you will see that the structure will start oscillating also in another mode. Earlier it was moving in this mode, it will start oscillating in this, and it will uh, produce some whirling kind of motion. Okay, so that is a non-linear mode. That is a non-linear effects that you get, and that way you see at the smaller excitation you get nice curve, but as you go on increasing this, it will go as a duffing kind of response, and as you go even more, you see that you have a non-planar kind of motion coming into picture. Okay, so that's how basically this is a non-linear response, and for more excitation you will have this kind of motion coming into picture where the combination of both the modes are there. Okay, so you can refer this particular paper for more detail. So similar to that, for single beam that we discussed, if you try to make use of arrays of beams, okay, what is the use of the arrays of beam? The arrays of beam, they can increase the sensitivity, they can increase the operating range, they can improve the scanning rate of some of these probes, they can improve the signal to noise ratio, and it can also be integrated well with the CMOS technology. And here one can utilize this linear nonlinear coupling in this range. So using this, one can make use of such kind of arrays and try to understand. And so this is another example. Here we can see for the arrays, if you try to excite them parametrically, you can see that how the response is tuning, and then there is a opening of the band. So it means that your device can work over this big range of uh, frequencies, right? If you operate it somewhere here, it can uh, you know work over this big range. So that's what the advantage of, you can open up the range of excitation operating range of these devices if you operate it in the form of arrays. So here is another example. This is a single beam. As I explained, you have one frequency which is increasing, another reducing, and then you are having this coupling range. If you are having three beams using the thumb, let us say if you are putting a laser from here to here, so you can see that for some of the beam, first it will increase, then reduce, then it will increase, and because as the position of laser go over it, so if it is over here, it will heat this one. If it is here, it will heat this one, and this will cool down. If it is here, this will cool down, this will cool down, this will increase. So as you go across this is what this is saying. So as if some structure is heated, we know that frequency reduces, right? So it will go, frequency reduces, and when it is away from it, frequency increases again. The same way it is happening, as the position of the laser is changing. So such kind of frequency change that you can see. And with the help of VDC, if you just keep the laser at one position and just vary the voltage, you see that for different beams you are having again, like this single beam, this is your single beam, like this you are having these two sets, this for one beam, this for another, this third, but there is a another crossing, that the other coupling points that is appearing. So one can make use of multiple coupling points if you can increase the number of beams in an array, and that way you can just see that there are a lot of coupling crossing happening. So it means you can really operate your structure over these many, so much of range, right? So modeling, as far as the modeling is concerned, there are two effects that we need to record while we do modeling of these electrostatic forces. And when you do that, many interesting thing can be done. And if you want to do computation, you can use COMSOL and try to know this electric lines, right, how they distribute across it, and then based on that one can figure out we in fact we came up with some modified forcing in the combined effect, and then we wrote this equation of motion. This is for mode 1, so let us say y, this is for uh, another direction, the motion in another direction, and here you see there is a coupling happening because of the stretching effect. Okay, so when you solve it, what you really get is something like that, this that I was talking about. One is going like this, another is like this, and it can also help you to increase the operating rate. Generally what happens whenever you apply VDC, after some time this will stick to the substrate, that is called pull-in effect. So if you are operating with the help of the coupled this mode or this mode also, you can delay that, you can increase this pull-in voltage, and that is very interesting observation. Similar to that, the arrays can also be modeled and you can show all these effects that can be uh, captured. Okay. And here you can see some nonlinear effects. So this is your external excitation, this is your parametric, this is combined uh, external and parametric. All these results are published, you can see these papers which are there. Then uh, more interesting effects you can find. So here you can see such, this is your linear frequency tuning, and at each point where they are separate from each other you can have your nonlinear response and parametric response like this. But when you come to this coupled region, you can see that there is a nonlinear response. When the quality factor is high, this appears like this, and so one of the mode will be this, another mode will be this, and when there is a low Q, you get a response of this kind, right? So many different kinds of nonlinearity can be obtained using all this frequency tuning, and many things awaits. So there are a lot of things that you can do. Then we also try to do tuning by varying the width of the beam. This is your beam and this is your width. From the top, if you see, the width will vary like this, right? So you can write all these equations. I don't want to go into them because we don't have much time. So you can vary it linearly or non-linearly. So these are converging beams, they are diverging beams, right? So with these combinations you can just try to you what will happen, area will change, right, and I will also change because of this converging and diverging width. And if you just try to solve for the frequencies and all, you can follow the usual standard technique. So here you see the first three modes. This is numerical modes for uniform beam. This is linearly tapered beam. This is quartic tapered beams, right? So you can see that these are the corresponding three modes. and there is a change in the frequencies also as the tapering modes vary. Okay, so that I will just show here. So what is really happening? This is very important figure. So what happens? So this is when you are uniform beam. Okay, this is uniform beam, and when you are having diverging beam, which is non-linear diverging beam, so you get a frequency change from here. So it reduces, right? If it is diverging, it reduces. So you get this much change. For linearly diverging, you get this much change, right? Now, if you take converging kind of beam, so for linearly converging, you will get this much change, and when you take non-linear converging, you get a change which is much more. Okay, so it means that the frequency can be tuned from here also, and that way one can make use of such kind of converging diverging combination to get lot of frequency tuning effects, and that's what we uh, utilized in terms of mass sensitivity of these sensors. Here we can just see that if you make use of uh, like converging beam, so sensitivity of this mass sensors increases like anything, right? So these are some of the factors that can be utilized, and again we tried to fabricate these structures, and then we did measurement using this laser vibrometer that we are having, and then you can capture the mode and do the measurement. If it is in the form of array, you can also do this measurement, and that way then we fabricated different types: uniform, linear, diverging, converging. You can see that we did measurement and we saw that this is how frequency varies. Okay, so in vacuum you see that the frequency varies from 80 kilohertz to, let us say, some 10 kilohertz. Okay, so it means you are having 70 kilohertz operating range that can be tuned by just varying the tapering ratio from zero point 0.5 to minus zero point 0.5. So this is diverging, plus is diverging, okay, and this is converging. So by combining this, that much of tuning can be achieved. If you do the same measurement in ambient, then you see that there is a less change that is coming. So, oh, I'm sorry. One is your quartic, not so they in ambient and vacuum, both of them came out to be same. But one is this is your linear. I'm sorry. This one that you see. 1 minute. Yeah. So this one is your linear tapered. This is your linear, and this one is non-linear, which is quartic one. That's what. So this is your quartic, and this is your linear from here. Okay. So the linear will not give you much change. The quartic one will give you, which is non-linear variation, will give you a lot of change. And the damping also, the changes that you can see in linear and non-linear, and with respect to that, you can couple two of them. One can be your converging, one can be your diverging, and with that you can just see that how the difference between them can be tuned. So here you can see quartic converging, linear converging, linear converging, uniform, or a combination uniform and linear converging. So all this combination you can have, and you can attain this gap between these two modes, because you are having two members, so you will have two modes, right? One is in phase mode, another one is out of phase mode. So the gap between them can be tuned by taking different combination, and that's what we did this study. You can find this one over in this paper. Even we try to figure out how the changes happen when you have a number of these beams varying. Another interesting thing you can think about, uh, these combination of letters. They are coupled kind of, right? They are like a coupled beams, so you can write your A B C D, right? And you can see that it oscillates like A, it oscillates but like B C D. The only thing is that you will have to make it free at the other end. Okay, otherwise it will not give you a proper vibration. Even you can make a word like IITH. If your coupling is not proper, you will not get the proper deflection. If the coupling is proper, you get very nice deflection, right? So that way one can do all this. There are many challenges, as I said, lot of, I have talked about all this, and there are couplings. So I will not go into detail of many of these. I'm sorry, I just scrolling down here, but 1 minute. Yeah, I'll finish it over here. So there are a lot of interesting challenges. One is non-linearities, right? Another one is coupled field. Third one is what are the microscale phenomena that are there. So all of them you need to tackle while you do modeling of these MEMS devices. So with this, I would like to stop and open the session for some question and answer.
Hello.
Yeah.
Uh, Hello. Thank you so much, sir, for this wonderful session. There is one participant asking for development to repeat the development of cycle MEMS part.
Deb,
So please give some comment on it. Development of cycle MEMS.
okay. This one, development cycle of MEMS.
Yes, sir. Development cycle of MEMS. Yes.
So that's what I discussed, that first we need to decide what we are going to fabricate for. So whether you are going to use MEMS as a mass sensor, temperature sensor, pressure sensor, and based on that, you will have to decide how much small change you want to measure. So after you decide it, you correlate it with the corresponding frequency of that, and based on that, you can fabricate your device. Okay, so that's how we design it and then fabricate it, and we do testing, and that's how basically it goes on. So if I understand the question, is this what he's asking, or is he asking what is the development stages of, like what is the current stage of MEMS?
Hello. Akash, sir, can you unmute yourself and ask if is there any information you needed? Okay. Is there any other question from the participant? They can unmute yourself and you can ask your question. I think no any questions from participant now, sir.
No problem.
Okay, thank you so much, sir. Yesterday also, your session
Mm.
was on fundamental of vehicle dynamics. It was
Mm.
wonderful session, and today also you have talked about talked on linear and non-linear frequency tuning in MEMS. So
Mm.
actually, you have covered many things graphically as well as mathematical, all mathematical equations. So many technical terms, related terms you have explained, and it was wonderful experience actually. And you have
Thank
covered
you.
many things like development of cycle of MEMS, design stages, fabrication stages, packaging stages, and many more. Thank you so much for this wonderful
Thank
session,
you.
sir.
Thank
Thank
you
you
very
so much.
much for the opportunity. Bye. Take care.
Thank you. Thank you, sir. Bye. There is one announcement for the participant. Next session will be start at 3 p.m. Please join at 3 p.m. Thank you. Thank you, everyone.
Thank you, sir.
Thank you, sir.